Jnanam paramam dheyam. Knowledge is supreme.
Let us look at R3 for example, or RD. Polynomials of degree less than or equal to 3. Is it finitely generated? So, let us look at it. Okay. So, let us look at this example. So, we are looking at R3x. What are elements of it? They are polynomials Px. And what does the polynomial look like? So, that is a0 plus a1x plus a2x square plus a3x cube, where these ai's are, let us say we are taking real. So, they are real entries. Is okay? That is what polynomials look like. So, clearly Px is already a linear combination of what? Constant 1 is a0 multiplied by 1, a1 multiplied by x. So, if we treat x as a polynomial, right, is a polynomial degree 1. So, this belongs to the set, okay, 1 x Px belongs to the span of x square x cube, right, because that is the way we write polynomials, right. Okay. So, Px belongs to this. So, that means what? Every element of, so that belongs to Rx. So, every element is a linear combination of 1, 2, 3 and these 4 elements, right. So, that means what? R3x is finitely generated, is okay. Finite number of them. If I take this finite 4 of them, every element is a linear combination of them. So, this is finitely generated. Same will be say C3 or any RD of x by 3. I can take any degree, right, any degree D is again finitely generated. What about Rx? That is a space of all polynomials. Is it finitely dimensioned? It is finitely generated. Is it finitely generated? Yes. Can finite number of polynomials give you all polynomials? So, let us take Px, let us say P1x, P2x. So, suppose P3x, some finite number of them. So, Pnx, they generate all. So, let us assume finite number of polynomials generate everything, right. We are trying to test whether this statement is true or not. Let us say this is true, right. Now, P1 has a degree, P2 has a degree, Pn has a degree. So, let us take m to be equal to the maximum of degree Pi of x. I 1 to, we have taken n. Take the maximum of these degrees. It is a finite number only, right. This m will exist. So, consider say qx a polynomial such that degree of is equal to m plus 1, right. Rx is all polynomials. So, pick up any polynomial of degree. So, for example, I can take qx to be equal to x to the power m plus 1. itself, right. So, the question is q x an element of, let us call this span of, this span we something. So, this is W, the span of P1, P2, Pn is W, claim was W is equal to R x, right. So, this q x belongs to W, right, q x belongs to R x, right. So, implies, so question is, does this belong to W? If it belongs to R x and if R x is same as W, then it should belong to W, right. So, if yes, that means what? That means x to the power m, say let us say plus 1, if we were taken this one, should be equal to some alpha 1 p 1, right. It should be a linear combination of this plus alpha 2, I am just spreading, I am not right, okay, let me write x also, plus alpha n p n x, right. That should be true. Now, on this side, what is the degree of the right hand side? It is a polynomial. In the right hand side, what is the degree? M is the maximum, right. So, degree of this right hand side is equal to m. What is the degree of left hand side? M plus 1. So, this is a contradiction, right. A polynomial of degree m plus 1 cannot be equal to a polynomial of degree. See, the basic idea is if you take finite number of elements in R x, then there will be maximum degree of all of them. So, what they will generate is, at the most they can generate only polynomials of degree, maximum degree, that is m. They cannot generate something bigger than that. Clear? Because when you add linear combination of polynomials of degree less than or equal to m will be again a polynomial of degree less than or equal to m. It cannot be bigger than m. So, no finite number of polynomials in R x will generate the whole of R x, right. That means, R x is not finitely generated. Each R n x, each R d x is finitely generated, but when you take the union of them, that becomes a vector space which is not finitely generated. Is okay? Clear? Okay. Actually, we can write something in fact. So, let us write in fact, if I write S which is 1 x, x square, x n, if I take this set which is a subset of R x, it is not a finite set, it is an infinite set, right. Then the space spanned by S is equal to R x. They will generate R x. If I stop somewhere, that will not, that is what just now we showed, right, because if we stop somewhere, there will be power will be some m, right, higher degree will not be generated, but this will generate now. Why? Because if I take any polynomial in R x, it will be a polynomial of some degree, right, say n, then 1 up to x n will, a linear combination will give me that polynomial. Is that okay? Right. So, actually we have got a set of generators which is infinite. We have got a set of generators and no subset of that will generate it, that also is clear, right. Actually, no finite subset of R x will generate R x. Okay. So, and we have got a set of generators which is infinite and generate. So, R x is a vector space which is non finitely generated. You can call it, if you like, is infinitely generated, right. So, not finitely generated, this is one example. Can you think of some other example of a space, vector space which is not finitely generated? The idea should be, see, if you take a vector space which is finitely generated and take a subspace of it, that also is going to be finitely generated, right. Now, if you take a vector space which is infinitely generated and put it inside a bigger thing, that bigger cannot be finitely generated, right. So, let us think of polynomials as functions, right. Each polynomial p x, so you can think x varying in x is a variable, you can think it varying in 0 to 1, right, interval 0 to 1. So, here is something which you will find useful, namely let us think of p x as a function for x belonging to 0 to 1, right. That means what? P is a function from 0 1 to r, right. So, let us just look at, so what is p of x? Is a polynomial of some degree, right. So, let us say it is a 0 plus a 1 x plus a n x to the power n, where a i's belong to r, right. So, instead of treating p x as a polynomial, a quantity which is just a linear combination of this kind, we treat it as a function. So, do you think this p is continuous? Now, a bit of calculus is coming. Is this polynomial as a function on 0 1 to r, is it a continuous function? Yes, it is, because constant is a continuous function, this is a continuous function, x to the power n is a continuous, sum of continuous functions is continuous. So, this p which is a polynomial on with x varying in 0 1, I can think it as a continuous function in 0 1, it is an element of C 0 1, the set of all continuous functions, right. Now, this itself is a vector space, given two functions on 0 1 taking real values, I can add them, right, f x plus g x, that is f plus g, scalar multiple of a function alpha times f is defined at x is alpha times f of x. So, this itself becomes a vector space if I treat addition of functions and scalar multiple of functions as operations, right. So, then polynomials, so then R x sits inside C of 0 1, here I am taking this polynomials in 0 1 only, x varying in 0 1, right. So, space of all continuous functions is again a vector space in which sits inside it a subspace of infinite generation, right. So, C 0 1 cannot be finitely generated, so that is again infinitely generated, right. So, that is another example. So, what I am trying to say is that vector spaces which are not finitely generated are of importance, that is why one should be studying what are called abstract vector spaces, right. So, let us look at some more. Then what did we do? We looked at what is called linear independence and dependence. Same you can define, you can say finite, given a set of vectors or finite set, you can say they are linearly dependent if a linear combination is equal to 0, where all the scalars are not equal to 0, at least one of them should be non-zero. So, there is a linear combination which is 0 with one of the scalars appearing non-zero, then you say it is linearly dependent set. Contrapositive of that, something which is not dependent, it is independent, right. So, what is linear independence? If a linear combination is equal to 0, all scalars must be equal to 0. Now, here for a given set, it is not necessarily that set should be finite. So, keep in mind. So, what I am saying is the following: if S is a subset of a vector space V, S any set, of course non empty, say S is linearly independent, this set is called linearly independent if for every V 1, V 2, V k belonging to S, k could be any number, you choose any finite number of elements of S, right, such that alpha 1 V 1 plus alpha k V k equal to 0 should imply alpha I equal to 0 for every I. right. We are not saying S itself is a finite set, S could be any set. Any set of vectors will be called linearly independent, is called linearly independent if you pick up any finite number of elements of that set S, take a linear combination of the finite number, because linear combination is defined only for finite. If that is equal to 0, implies each scalar is 0, then that set S is called linearly independent. Is it clear? Okay. So, let us even before going further, let us look at some example. Okay. So, let us come back to that our friend which have been giving us many examples. Let us, right. So, this is a vector space. What does P x look like? P belonging to R 3 x implies P of x is equal to A 0 plus A 2 x square plus A 3 x cube, right. That is what it looks like. Okay. Now, so let us write S is equal to 1 x square and x cube. So, claim that this S is linearly independent. This is a linearly independent set. So, for that what we have to check? Take any one of them, two of them, three of them, all of them, does not matter what you take. So, let us take all of them, right, that will cover everything. It means if alpha 1 times 1 plus alpha 2, so alpha 0 times 1, alpha 1 times x, that means what? Alpha 1 x plus alpha 2 x square plus alpha 3 x cube equal to 0 for alpha 0, alpha 1, alpha 3 belonging to R should imply alpha I equal to 0 for every I, right. That should happen. Now, if this equation is satisfied, okay, that means what? What is the meaning of this? Let us look at that. Is what is given to us. What does this mean? That this is equal to 0. Left hand side is a polynomial, right. What is the right hand side? What is 0 on the right hand side? You can't have a polynomial equal to 0 on one side, a polynomial other side a number. Equality of two same things, similar things make sense. So, what is written here is, which is not normally mentioned or understood, is that 0 is a polynomial, the 0 polynomial, right. So, it is 0 times plus 0 times x plus 0 times x square plus whatever you want to write it. So, this right hand side is the 0 polynomial. If that is a 0 polynomial, that is equal to this polynomial. What does equality of polynomials mean? When do you say two polynomials are equal? If the like power coefficients are equal, right. So, this star, so note star implies coefficients of like powers are equal, and that means that each alpha I is equal to 0 for every I. That is by definition itself of equality of polynomials, right. That itself implies it is 0. So, this set 1 x square x cube, right, is a linearly independent set in the space of all polynomials of degree less than or equal to 3. Okay, clear?